Okay, so we're on to the last major part of steel, and this is where everything kind of comes together. It's also where things tend to be fairly straightforward, because it's a lot of, here's the effect of these alloying elements. Here's these, these processing operations, right? So previously we talked about all the different phases in steel, the physical metallurgy of their formation, and we cursory mentioned, yeah, these alloying elements have these effects, right? But it's hard to put all that together, right? If I say the effect of molybdenum, right? We talked about how it moves different phases, the kinetics, how it alters them in different ways. We need to think about all of that together, right? And how does the alloying and the processing and the structure give us our properties, right? And this is, unfortunately, material that's not available in a lot of books and reading anymore. There's Harry Badisha's book on steel and steel processing, which has a lot of this in it, but that's a lot of material to get through for the purposes of this. So when I was preparing for this, more than one person recommended this Professor Kumar's course. Where is he? He's at Veer Surendra Sai University of Technology. All right? But anyway, I went through all of his course notes, and I was fascinated. This is like the best collection on fundamental steel processing that I ever came across. He's got a full semester course, 800 slides on the heat treatment of steel, right? He basically has one course, just heat treatment of steel, right? This is something that like when we had a metallurgical degree, right? We had courses like this, but nowhere in the U.S. could a course like this actually be taught anymore, right? This focused on one, just heat treatment of one metal system, right? So I encourage anyone who is doing anything with steels to go look at his notes, right? And as kind of as I was putting this together last year, I started to use his notes and type up my own, and realized I was doing so much essentially transfer from his slides to mine that it would be completely unfair for me to like pass this off as my own lecture notes. So essentially, when you see the ones that are in this color scheme here, these are slides that I directly took from his notes wholesale, right? And so I want to be very honest about this because these notes are fantastic. And I thought, so I interjected other content, right? So when you see things in the blue font and the stuff that looks like the other notes is stuff I added in, right? There's added content here. But yeah. Okay, so let's go back to our classification that we talked about in the beginning, presented in a slightly different way. We can break down steels generically into low alloy and high alloy steels, right? And then further break it down into low carbon, medium carbon, high carbon, right? With plain carbon steels can either be low carbon, medium carbon, or high. And then we have the low alloy steels, which if they're low carbon tend to be called HSLA or high strength low alloy. Medium carbon low alloy steels tend to be called heat treatable steels. And then low alloy high carbon steels generally fall into the category of what we would call tool steels. All right, so this is just sort of nomenclature. the main alloying elements that we're talking about for each of these with low alloy steels are going to be chrome, vanadium, nickel, and molybdenum. Right? And as we go across, with the exception of high alloy steels, talk about that, the cost gets more, the strength gets more, and we lose our ductility. Right? We have this inherent trade-off between ductility and strength, and steels are no different. So hardenability, right? How much can we strengthen? Right? Tensile strength and elongation. Right? Percent elongation. Right? So strength and ductility and what they're used for. Right? High alloy steels either tend to be tool steels or austenitic steels in the stainless when we have significant amounts of chromium. Right? These also tend to be steels for things like creep applications and creep, corrosion, high temperature. Right? So nothing new here, just presented in a slightly different way. We'll be talking about the temperature points, right? So just a refresher of where they sort of are on the phase diagram, right? Okay. And so the first thing we want to look at is all of the alloying elements. Where will they tend to go? Where will they tend to partition? What phases will they stabilize? What phases will they destabilize? Right? And so our austenite stabilizers, the important ones, manganese, nickel, cobalt, copper, and zinc, right? So these stabilize the gamma field, right? These tend to have a FCC crystal structure, right? So they're more soluble in ferrite, right? And when they're in a two-phase equilibrium, they will tend to segregate in austenite in preference to ferrite, right? So these are the substitutional solid solution alloying elements that are going to stabilize austenite. Carbon and nitrogen, the interstitials, are also austenite stabilizers, as we said before, because the interstitial sites in austenite are bigger than they are in ferrite. Right? We got a whole mess of ferrite stabilizers. Right? There's a couple oddballs. Right? We say these have a BCC, tend to have BCC structures. Well, okay, aluminum is not BCC, right? But we know aluminum has a high pressure BCC phase. Beryllium is HCP, right? Niobium is BCC. Tin is BCC or HCP, right? Titanium's HCP. So it's not as clear cut. So just because something's FCC doesn't automatically mean that it's going to be an austenite stabilizer. Right. But these elements are going to strongly segregate to ferrite and stabilize. Right. Chromium is a special case. Chromium at very low concentrations, it will stabilize ferrite, but at high concentrations tends to stabilize austenite, right? So austenitic stainless steels tend to have a high percentage of chromium, right? So chromium's a little weird. Okay. So you can see stuff that I added in, right? in between the other nodes. So we can think about the effect of alloying elements as to how they're going to change the phase diagram, right? So class 1 sets of elements, nickel and manganese, are the prime ones, but, right, a bunch of other ones, cobalt, but, you know, ruthenium, palladium, osmium, iridium, and platinum are not typically in commercially available alloys, so we don't need to worry so much about them so much, right? But they create what's called a open austenite field, right? So where is austenite on this phase diagram? Right, so it's this region here, right? So up here is the paratectic point. Here we normally have a eutectoid, right? It's absent, right? And so if we're at kind of a high enough concentration, we can go completely austenitic down to room temperature, right? We can eliminate the crossing into the ferrite region, okay? Class 2 is an expanded austenite field, the addition of more copper and nitrogen, right? So we have here, we've got an austenite region that is significantly larger than would be with just small amounts of carbon, or significantly larger than it would be for pure iron, right? And we have the closed austenite field. So where's austenite in here, right? So essentially the delta iron and the ferrite, both BCC phases become connected, right? And this is our region of austenite stability, right? So a lot of elements will tend to do this. Strong carbide formers, right? So titanium, vanadium, molybdenum, chromium, right? And then ferrite stabilizers, silicon, aluminum, beryllium, right? So this is a common type structure. And then a contracted gamma field, boron and other strong carbide formers. This loop becomes contracted, but we often have other phases that form in here, right? So we have intermetallic compounds that can form with iron in these alloying elements, right? So these are the general classes. If we look at specific points, right? If we look at the eutectoid composition, all the elements tend to lower the eutectoid carbon content, right? So if we have other stuff in there, what do I mean? What do we mean by lower the eutectoid carbon content, right? So this is the eutectoid point. This is the carbon concentration. If we have other alloying elements, we're going to shift the eutectoid point over to the left, right? Titanium and molybdenum are very effective at lowering it, right? And we'll take a look at exactly what happens with the different phases under the influence of titanium and molybdenum in a minute, right? But if we have a steel with 5% chrome, it has a eutectoid point of 0.5 compared to a 0.8% eutectoid point for plain carbon steels, right? High-speed steel, which is a tool steel, right? So high-speed steels fall under these type of compositions, right? The eutectoid point is shifted all the way over to 0.25%. So that's the eutectoid composition. On the eutectoid temperature, right, any austenite stabilizers are going to lower the eutectoid temperature, right? Ferrite stabilizers will always raise the eutectoid temperature, right? So generally, whatever you put in there is going to shift it to the left, but whether it's more if it likes ferrite or austenite, it's going to shift it up and down, right? Okay. So we can look across all the alloying, all the elements, and look at the relative strength of austenite or ferrite formers or stabilizers, right? The interstitials are very potent, and then what we had mentioned before, right? Our FCC. In terms of ferrite stabilizers, many more alloying elements tend to stabilize ferrite than austenite, with zirconium and titanium, right? And hafnium as well. So the group 4 transition metals are by far the most potent ferrite stabilizers, right? These all have their HCP, but they also have cubic forms as well, right? Which are BCC. All right. So just looking at the relative magnitude of how well they are. So manganese is an austenite stabilizer, and so we can see here's just an outline on the phase diagram of the austenite field by itself, with all the other lines taken off, right? And if we have 0.35% manganese, this is what it looks like. If we expand to 6.5%, right, we've dropped the eutectoid temperature, moved it over, and we've expanded the gamma phase field, right? Chrome, on the other hand, is a ferrite stabilizer. So as we add additional amounts of chrome, we shrink the size of the austenite phase field, right? And we still move the eutectoid point to the left, but now we increase the temperature, right? So these are the general trends that it's good to know, right? If you're thinking of alloy design. So titanium can essentially completely eliminate the gamma loop. 1% of titanium completely eliminates the austenite phase field, right? For chrome, you need 20% to do that, to shrink it down to a point on the phase, essentially a point on the phase diagram, right? So these group 4 metals, zirconium's even more potent, right? Significantly less than 1% zirconium will remove the. Right? Okay, so we want to think about, at the same time, what the alloying elements are going to do to all the reactions that we talk about, right? So if we think about pro-eutectoid ferrite reactions, right, meaning allotropomorphic or idiomorphic ferrite, right? We know that ferrite grows with the partitioning of the alloying elements between our ferrite and our austenite, right? And the rate is governed by the diffusion of the species, right? So we have either 2 cases, right? Depending on how slow we cool it, or if we can have a para-equilibrium where ferrite grows without partitioning of the elements, right? And our growth is going to be determined only by the diffusion of carbon, right? So if we're up here, right, we're going to partition. If we're cool faster, we're not going to partition, right? But we have to consider the effect of the alloying on what type of ferritic equilibrium ferrite reactions we're going to have, right? Manganese partitions, right, and it tends to slow the growth of ferrite compared to the iron-carbon boundary, right? Molybdenum doesn't partition. So at higher temperatures, growth rate is rapid, similar to the boundary, but at lower temperature, our partitioning solute collects at the interface and gives a solute drag and slows our growth down, right? So if we look at what this curve is telling us, curve A is just iron 0.5% carbon, right? And this is essentially the nose of our curve. We have manganese, we've got partitioning, it slows it down. And then with molybdenum, we expose the other region of our TTT curve. This is like the bainitic bay. This is the reconstruction. Up here we'll have ferrite pearlite. All right, so we're keeping the carbon concentration the same, but we're changing the alloying elements and drastically changing our CCC curve, TTT curve, CCT curve, right? And this is just at 1% of each of those elements. Well, this is a log time, so it's not really, it's an analog to that, to the cooling curves, right? So this is isothermally at a constant temperature, right? What are you going to hit? So I guess it's a TTT curve without a superimposed cooling rate on it. So think of this as a TTT curve.
Partitioning when it partitions, it can happen much faster. So it is towards but non-partitioning. If it partitions, it should take more time. If it doesn't partition, it should not take that much time. If it partitions, it should take less time.
Yeah, so I'm not sure I understand the question. So if it partitions, you
need some time to partition.
You need some time to partition, right? If you don't partition, the growth rate, right? No, if you don't partition, it stays the same composition. Your growth rate is limited by the diffusion of your slowest moving species.
No partitioning.
With no partitioning,
yes.
Right?
Yes.
So the interfacial growth rate is going to be limited by the jump frequency of your slowest, your heaviest element.
Which means the transformation will happen faster, right? Which means you keep towards the.
What's that? This is the total time of the reaction.
Isn't that just the start of the transformation? Those lines just represent the start of the transformation.
This is the nose of the curve, so it's like the 10%. The 10% reaction, right? So let's talk about it offline, and we'll come to a consensus. I'm not sure we're quite saying exactly the same thing, right? Okay. So the elements, of course, don't necessarily sit in isolation, right? They all have variable degrees of affinity with carbon, right? So we have to think about how likely are we going to form carbides in our material, right? So this is arranged increasing affinity for carbon, right? So zirconium, very strong carbide former. The iron matrix itself is a relatively weak carbide former, right? So if we had vanadium to a steel that has both chromium and molybdenum with insufficient carbon, the vanadium is going to remove carbon from the chromium carbide, right? And then reduce the molybdenum. Is it reduce? I got to think about which way my electrochemistry goes. If I remove the carbon, right? Iron. Okay, well, anyway, it's not oxidized, so it has to be, it has to be reducing. Right. So, but anyway, if we add vanadium to a chromium molybdenum steel, right? We're going to, and we have these carbides in there, we're going to form vanadium carbides, and chrome and molybdenum are going to go back into solution, right? So if you want certain elements to stay in the solid solution and not be removed through carbide precipitation, you need to have a stronger carbide former in there to guarantee that they're going to stay in solution, right? It's kind of like the concept of a sacrificial anode, right? Or galvanizing, right? You want something that corrodes much faster than the thing you're trying to protect, right? Okay. Silicon, nitrogen, copper, and aluminum are graphitizing elements, right? So they will interfere with the cementite reaction and enhance the transformation to the equilibrium graphite, right, phase of carbon, right? And this is really detrimental, right? So then you need a high degree of austenite stabilizers in there to counteract this effect, right? Because the ferrite, right, you don't want a ferritic pearlitic steel, which involves cementite for strengthening, right? You don't want all of that cementite to turn into graphite and lose your strengthening ability. Cobalt is the only common alloying element which is neither a carbide former or a graphitization enhancer. Right? Right. So again, there's a ton of information here, right? None of this is critical for memorizing, right? These are the kind of things you jot down on your sheet, right? Common austenite formers, common ferrite formers, right? So when you're looking at this, don't feel overwhelmed with memorization. A lot of this is, like everything else, a lot of this is important information to know, especially if you're going to be working with steels, right? But not necessarily important to know for the exam, right? Okay, so that's a lot of the general gist of common alloying elements. We're going to talk more about them as we go through, but not so much of a fire hose brain dump. The prior austenite grain size is actually one of the most important properties of steel, especially in steels that were martensitic and then tempered, right? The mechanical properties, particularly the fracture and fatigue properties of the final steel, are very, very strongly influenced by the size of the austenite grains, prior austenite grains, right? So the austenite grain boundaries, all of the pro-eutectoid phases, pearlite, bainite, right? We all talked about them nucleating at austenite grain boundaries, right? So does it make sense that if we have very coarse austenite grains, we have very different, much less grain boundary area, fewer nucleation sites versus a small grain, right, where we have easy nucleation of these phases? So if we want a fully martensitic structure, right, we can grow our austenite grains really large, and then we have less nucleation sites, right? So we can have a slower, retard the kinetics, the nucleation kinetics of all the other phases, and have a slower cool and still get martensite, right? That would be great, except the impact toughness of steel is very sensitive to the austenite grain size in the hardened and tempered condition, right? So fine grained steels have fine prior austenite grain steels have a much better fracture properties than coarse grain steels, right? So part of that is with segregation, and part of it has to do with the fact that fracture preferentially, the prior austenite grain boundaries are a crack propagation path, right? So if I have small grains, I now have a tortuous crack path rather than large, straight, simply connected fracture path, right? But there's some impurities, right? Tin, phosphorus, lead also, that's not listed here, but will segregate to the prior austenite grain boundaries and weaken adhesion, right? So that this intragranular fracture becomes quite brittle. We can also affect the martensite start temperature, right, with the decreasing of the austenite grain size, right? Remember that I talked a lot about the plastic accommodation of the martensitic shear transformation, right? So essentially what we have is a Hall-Petch effect. The smaller the prior austenite grain size, the higher the yield strength, so the harder that martensitic shear is to accommodate, so it stabilizes the martensite, reduces the martensite start temperature, stabilizes the austenite, right? So there's a lot here, right? But this is basically just schematically, right, of what happens with the microstructure on heating, right? So the upper critical temperature, we have a fully austenitic microstructure. At the higher we go, the austenite grains are going to grow, right? And of course, the driving force for this is just curvature-driven grain boundary growth, right? And we can grain coarsening will occur, right? And the driving force of this is just the stored energy of the grain boundary energy, right? We talked about this at the very beginning of the class. So depending on the alloying composition, the ease at which this austenite grains grow, right? We can classify things into inherently fine grained or inherently coarse grained, right? So inherently fine grained steels will resist the growth of grains in the austenite field, and we'll talk about grain refiners in a little bit. But if you have alloying which gives you sufficient grain boundary pinning that you retain a small austenite grain size, right? Inherently coarse-grained steels, we've got high processing temperatures, so the grain growth is very fast, right? So what's our strategy for pinning? We want what size particles, right? We want very small particles, right? The nanometer size particles and submicron dispersions, the same as with aluminum, right? We want precipitates of oxides, carbides, and nitrides, which are going to pin the grain growth, right? And if we can make the solvus of these particles high enough, right, then we can go high into the austenite phase field without them dissolving, right? So, right, but if they do dissolve, right, the particles are going to have no result, no more resistance to grain growth. Okay, where are we? Just thinking about where I want to get to today. Oh. That's out of order. Okay. Making sure okay. I'll have enough time to get to where a good breaking point is going to be. All right. So here we have schematic Ttt diagrams. All right. So we can have various types. Plain carbon tends to look like this. Austenite, this is the start of pearlite growth. And here's our pearlitic microstructure. Right? If we can reduce the martensite start and push the bainite start over, we get this two bay. Right? We have the pearlite bay and the bainite bay. Right? This, unfortunately, is pretty hard to do. We don't have a lot of steel compositions that have TTT curves that look like this, but this would be great because just depending on your cooling rate, you can either get fully martensite, fully bainitic, or fully ferritic pearlitic steel just by at the same compositions with just controlling the cooling rate. A lot of alloying elements, right, will shift our martensite start down and shift up our pearlite bay. So essentially, we're missing our bainitic region. Or here we have a type of TTT curve without the bainitic region, right? So these are just sort of schematics, right? Just back in the same way as I talked about schematics of the 4 different types of phase diagrams you can have with the gamma phase field. Here's just 4 different schematics of TTT diagrams for alloying steels. So what alloying elements are going to give you these different regions, right? Which elements are going to push which reactions which way, right? So we can think about what's going to increase the stability of our austenite region, right? So we had a long list of austenite stabilizers that are going to retard the pro-eutectoid and pearlitic reactions, right? And shift the TTT curves to the right or longer time scales, right? So the mechanism for this is just the low rate of diffusion of the alloying elements in the austenite, right? They're substitutional. These are all substitutional elements, right? They also tend to be carbide-forming elements, so they're going to reduce the overall diffusion of carbon necessary to create cementite, right? And we have solute drag on the austenite-ferrite interface, right? So a lot of what we put in is going to push this over to the right, right? And this is what I was trying to sort of get across with the other slide, but not jump the gun a little bit. Okay. So we've got a whole host of elements here that expand the stabilized austenite phase field. So this is going to depress the position of the TTT curves to lower temperatures, right? But the ferrite stabilizers are going to raise the eutectoid temperatures and the TTT curves, right? So if something, right? So ferrite stabilizers move the TTT curve up, right? Same as on the phase diagram. The eutectoid temperature moves up, the curve on the TTT curve also moves up, right? It seems common sense, but until you actually think about it for a second, it's not immediately obvious to a lot of people. Okay. Aluminum, cobalt, and silicon accelerate the nucleation of ferrite and pearlite, so they're going to shift the TTT curve to the left. Right? They're going to shift out the nose of the pearlite bay, right? Because they're accelerating, making pearlite nucleation and growth easier, right? So we have complex diffusional effects, and because of that, we can separate out this pearlitic and bainitic curves for different elements. And as we had mentioned before, I showed this, if not this exact equation, but something similar, right? This is the effect at altering the bainite start temperature. So where the bainite curve is going to be, and that's going to be contributing, not competing, that's the word I'm thinking of, competing. I almost said collaborating with, competing with the martensite start temperature, right? So how do the same elements affect the martensite start, right? So it's a balance between this, whether or not you can expose the bainite bay based on the elements that you have, or whether it's going to be too far back, right? And you can't get it out past the nose of the pearlite, and you're going to come down into the martensite start. All right. And I think we will, got one last thing, and then we'll stop. right? So I had mentioned grain size before in terms of properties, but grain size also is going to affect the kinetics because of the more grain boundary area, right? So finer grains will tend to shift the nose of this TTT curve out, right? And remember, these are plotted, and this is log time, right? So the effect is on a linear scale is much larger than you would expect, right? And so grain size will shift. Also, heterogeneity is important, right? If you have the grain size of your austenite is highly heterogeneous, right? So say you have a partially recrystallized structure with many small grains and many large grains. You're going to essentially spread things out. You're going to have TTT curves where the start to finish is going to broaden, right? Right? And it has to do with grain size, whether you have undissolved secondary phase particles, grain boundary refiners, right? These things can all retard the Pearlite transformation. But the key thing is that the effect of having a heterogeneous structure doesn't necessarily shift the whole curve over. It spreads it out, right? So you'll be starting earlier but taking longer to finish, right? For the same mean grain size as if you had a homogeneous, small, tight, standard log normal grain size distribution, right? It's kind of a minor point, but well, because so you have a range of very small grains and a very large grains, right? So small grains, the effect that we said was to shift it out because you've got more nucleation sites to shift it to the left, right? So those small grains, nucleation will start earlier, right? But the big grains will take longer, right? Whereas if I have a narrow, well-controlled grain size distribution, all the grains will nucleate at the same time and they'll all finish at about the same time. If I have heterogeneous, some will nucleate earlier, and then the big grains will take a long time to finish. So instead of having a tight set of curves here, right, this is like the 10%, and then the 90 would usually be like right here. Now the 90 is back here because you got to deal with the big grains as well. Okay, so that's a lot of stuff on alloying, and I apologize for the brain dump. It's kind of boring. There's not a whole lot to make it super interesting. It's kind of like, here's what this alloying element does. Here's what this alloying element does. Don't memorize any of that nonsense. Just write down, right? Make sure you understand the trends enough that if you have them down on your sheet, you'll be able to quickly access and understand and use it for the exam.